This video is produced by Sammy and
Kevin Burgess
for by Inquisition Press to support the workbook Sophomore Organic Chemistry 2 by Inquisition, available from www.byinquisition.org.
So we've learned that when nucleophiles approach an aldehyde or a ketone, they attack the carbon of the carbonyl. Now, to activate a carbonyl to a nucleophilic attack under neutral or acidic conditions, we protonate it first. Nucleophilic attack on ketones and aldehydes gives tetrahedral intermediates. In this case, where we've formed tetrahedral intermediates from 2-butanone, this one on the left corresponds to attack of
Methylamine?
And since this one has all carbons, that must be formed from the
Grignard.
The next one is formed from
Hydrogen cyanide?
hydrogen cyanide, very good. And the last one is from
Pyrrolidine.
the mechanism of reaction of aldehydes and ketones with amines or with cyanide involves first protonation of the carbonyl, addition of the nucleophile, and then in the case of cyanohydrin formation, we just protonate the oxygen. That mechanism would apply to almost any aldehyde or ketone. The reactions can be reversible, but they all proceed in the same way under acidic or neutral conditions. When aldehydes or ketones react with amines, the first step is similar. It's always
To protonate.
protonation, yes. So these reactions, condensations of amines with ketones and aldehydes, proceed quickest under acidic conditions. Protonation of the aldehyde or ketone, what does that do to its reactivity?
It increases its reactivity.
Towards nucleophiles, good. And we can add a nucleophile, form a tetrahedral intermediate, proton transfer from the nitrogen to the oxygen, gives us another tetrahedral intermediate, and then pushing the lone pair from the nitrogen in towards the carbon releases water. Finally, loss of a proton gives us an imine. So you should be able to draw formation of an imine from cyclohexane carboxaldehyde, from benzaldehyde, and the reaction is fastest at pH 4 because at that pH the oxygen can become protonated, but the amine isn't protonated all the time. It's not locked up totally. Reactions of secondary amines with carbonyl compounds proceeds in the same way. So tell me, Sammy, addition of a proton will
Protonate the carbonyl oxygen.
and then the amine.
Will add as the nucleophile.
After that, we get loss of proton, gain of proton. What did they call that?
Proton transfer.
Proton transfer, good. Proton transfer, and then you've got to imagine the lone pair pushing out the protonated oxygen. In other words, we just release water in a
Condensation reaction.
condensation. Great. Now, at this stage, there are no protons on the iminium formed from a secondary amine. So the mechanism has to be different here. If there's no alpha CHs, the mechanism stops at the iminium. But if there's an alpha CH, that can be lost and we form enamine. On the next page in my book, page 71, the issue here in this question is recognizing that when a secondary amine attacks an aldehyde with an alpha CH, it will form an enamine or an imine.
An imine.
Enamine.
Enamine, that's right.
Enamine, because you form an iminium and then lose a proton. When I add a primary amine to an aldehyde, I will form an
Imine.
imine. So 2-pentanone reacts with this aromatic amine to give us an
Imine.
and if I add a big excess of a primary amine to a dialdehyde, I will get
Also an imine.
twice a diimine. Yes, good. But if I add a secondary amine, remember, to an aldehyde, the product is an
Enamine.
excellent. Nature uses this type of transformation quite a lot. There's a cofactor called PLP, which becomes bound to the lysine side chain of an enzyme. An amino acid then can attack the imine to form a tetrahedral intermediate, Proton transfer liberates the PLP with an imine bond to the amino acid. And the one shown in my book is aspartic acid. So once we've got that imine, the enzyme can do something quite clever. It deprotonates the alpha carbon, pushes the electrons all the way through the pyridinium to form a dihydropyridine, and then that's protonated on the benzylic carbon to form an imine to the carbon that was the alpha carbon of the aspartic acid. Hydrolysis of that will give an alpha keto acid from the aspartic acid. So it's as if the PLP is taking away the nitrogen from one amino acid, and actually what it does is it shuttles it between different amino acids in the system.